Hello everyone, myself Nisha Bharti, and in this session I am going to present diversity techniques. First of all, I would like to discuss about some of the challenges in wireless communication. There is some of the challenges that is high data rate, seamless and high mobility requirements, spectral efficiency challenge that is 2 to 10 bits per second per hertz, frequency selectivity due to large bandwidth requirements, seamless coverage and support across different network devices and media forms, reliable communications, harsh wireless channel, scarce radio spectrum and energy constraint. Then here comes what is fading. Deviation or attenuation that telecommunication signals experiences over certain propagation media, that is fading. Fading may vary with time, geographical position and radio frequencies and is often modeled as a random process. In wireless system, fading may either be due to multipath propagation or due to shadowing from obstacles. Reflectors in the environment surrounding a transmitter and receiver create multiple paths that a transmitted signal can traverse. The receiver sees the superposition of multiple copies of the transmitted signal and each traversing a different path. In fading, each signal copy will experience differences in attenuation, delay and phase shift while traveling from source to the receiver. This can result in either constructive or destructive interference, amplifying or attenuating the signal power seen at the receiver. Strong destructive interference is frequently referred to as a deep fade and may result in temporary failure of communication due to a severe drop in the channel signal to noise ratio. Then here is the some diagram which is showing the wireless propagation environment. Here we can see this is our line of sight path and all these paths are our non-line of sight paths. These line of sight paths are these are the multi-path group, and these are here we can see there is observable change with increase in bandwidth. Here per path we can see that there is an angle spread. Then what are the types of fading? There are two types of fading: large scale fading and small scale fading. In large scale fading, it includes path loss and shadowing effect. In large scale fading, signal power will attenuate for large period of time. And under the large scale fading, we have two, path loss and shadowing. For the small scale fading, we can say our power will attenuate for a small period of time means power will fluctuate over a small interval of time. There is a under small scale fading, there are two types, multipath delay spread and Doppler spread. In multipath delay spread, there is again two types, flat fading, frequency selective fading, and in Doppler spread, again there are two types, fast fading and slow fading. Then what is the need of diversity? If a fading radio signal is received through only one channel, then in a deep fade, the signal could be lost and there is nothing that can be done. So, if one radio path undergoes a deep fade, another independent path may have a strong signal. Diversity is a way to protect against deep fades, a choice to combat fading. Powerful communication technique to provide wireless link improvements at relatively low cost. It provides two or more input at the receiver such that fading phenomena among these inputs are uncorrelated. Here we can see in this diagram, it is modulator and there is an n number of parallel channels are there. So, through these n number of parallel channels, we are transmitting our signals. And here there are unbranched diversity combiner. Then we will demodulate our signal and we will get our demodulated output signal. Here we can see that if our channels are highly correlated, then fading will be high. We can see in this graph the two signals are superimposing each other, and in this graph we can see that if our channels are uncorrelated, then the fading will be less. We can get our signal from any one of the channel. Then the types of the diversity. There are two types. One is macroscopic diversity and other is microscopic diversity. What is macroscopic diversity? It prevents large scale fading. Large scale fading is caused by generally shadowing due to variation in both the terrain profile and the nature of the surroundings. Large scale fading is log normally distributed signal. This fading is prevented by selecting an antenna which is not shadowed when others are. This allows increase in the signal to noise ratio. Long-term fading can be mitigated by macroscopic diversity, and these are applied on separated antennas site, like the diversity using two base stations. Then, what is microscopic diversity? It prevents small scale fading. Small scale fading is caused by multiple reflections from the surrounding. It is characterized by deep and rapid amplitude fluctuations which occur as the mobile moves over distances of a few wavelengths. This fading is prevented by selecting an antenna which gives a strong signal that mitigates this small signal fading effect. Short-term fading can be mitigated by the diversity using multiple antennas on the base station or mobile unit. Then types of diversity. First one is frequency diversity, then time diversity, polarization diversity, space diversity, then under space diversity. There are again four types. First one is selection diversity, second one is scanning diversity, third one is maximum ratio combining, and fourth one is equal gain combining. Then we will see about these types of diversity. What is frequency diversity? Transmits the same signal with different frequencies. Here we can see that frequencies are separated, and frequency separation should be more than the coherence bandwidth. In the time diversity, it transmits the information signal repeatedly at regular intervals. We can see that there is a separation in the time, and each time slots are divided into different groups. The separation should be greater than the coherence time. Now, polarization diversity. It uses antenna of different polarization, example horizontal and vertical. The antennas take advantage of the multipath propagation characteristics to receive separate uncorrelated signal. SNR is improved by up to 12 dB even in line of sight channels. Then space diversity, a method of transmission or reception or both in which the effect of fading are minimized by the simultaneous use of two or more physical separated antennas. Here we can see single input, single output, single input, multiple output, multiple input, single output, and multiple input, multiple output. This is the best one. Multiple input, multiple output. Here we can get our signal as uncorrelated, because at the transmitter side we have n number of input, and at the receiver side also we have n number of output. Then combining techniques. Selection combining. This combining technique is very simple and cheap. Receivers select branch with highest instantaneous SNR. We can see transmitter will transmit the signal and it will pass through the n number of channels, and with that n number of channels, SNR monitor will be there, and that will monitor the SNR values of each channel. Then what will be the highest maximum SNR? According to that, receiver will receive that signal only. Then feedback or scanning combining. Scan each antenna until a signal is found that is above predetermined threshold. If signal drops below threshold, then it will rescan. Only one receiver is required here, so less costly and still needed. Multiple antennas are used here. Here we can see there are multiple antennas, and here we are receiving the signals. Then maximal ratio combining. Combining all the signals in a co-phased and weighted manner so as to have the highest achievable SNR at the receiver at all time. Optimal technique to maximize output SNR. A mean of combining the signals from all receiver branches so that signal with a higher received power have a large influence on the final output. Here also we are transmitting the signal, and here we have n number of channels. So from all the channels we are weighted our signals, and then each signals will co-phased, and then we will get our received signal. Then equal gain combining. Combining all the signals in a co-phased manner with unity weight for all signal levels so as to have the highest achievable SNR at the receiver at all times. Phase is adjusted for each received signal so that vectors add in phase. Performance is marginally inferior to maximal ratio combining but superior to selective diversity. This is simplified method of maximal ratio combining. Here we are transmitting the signals. Here also we are using n number of channels, but here we are using the signals in co-phased manner but with unity weight. Then comparison of diversity schemes. Then space diversity, polarization diversity, frequency diversity, and time diversity. There are some advantage and disadvantage. Space diversity easy to design, and whereas disadvantage is hardware size could be large. Polarization diversity, no space is necessary, but disadvantage is only 2 branch diversity schemes are possible. Frequency diversity, any number of diversity are selectable, but here L times more power and spectrum are necessary. In time diversity, no space is necessary, but L times more spectrum are necessary. Then application. The major application we can see that in TDS OFDM. Here we are using a space-time frequency coding scheme. Performance improvement of the system with this method is theoretically analyzed and computer simulated. Here we can see by using this scheme we can reduce the computational load by about 70% in above system. Then the diversity is used basically to provide the receiver with several replicas of the same signal. Diversity techniques are used to improve the performance of the radio channel without increasing transmitted power. Equal gain combining performs very close to MRC, but MRC is the best technique as compared to EGC. Among different combining techniques, MRC has best performance but with high complexity, and selection combining has the lowest performance and the least complexity. That's all. Thank you.